Right, so we're going to continue on from yesterday. So yesterday we started talking about bipartite matching. Well, actually yesterday we mostly talked about matching in general, but by the very end I mentioned one theorem about bipartite matching, and that's where we're going to start. But so just to recall, so remember a graph G is bipartite if you can split the vertex set into two sets such that all the edges go from one set to the other. So if there exists a partitioning of V into sets, well, a partitioning, sorry, I'll just say AB of V such that every edge of G has an endpoint in A and an endpoint in B. Right, so the picture is, basically, so you have a set A, you have a set B, and all the edges go across. Right, so there's no edges up here, and there's no edges down here. And just a bit of terminology, so we say this partition, so it's convenient to have a name for it. So we say that AB is a bipartition of G. Okay, it's just going to be convenient to say let G be a bipartite graph and let A be a bipartition. Is that definition clear? Yeah, so yesterday, I just very briefly at the end of the lecture, I mentioned that there's this nice theorem called König's theorem for bipartite graphs, which connects the size of the biggest matching to the size of the smallest vertex cover, right? They turn out to just be the same. So König's theorem says that if G is bipartite, then nu of G equals tau of G, where, in case you don't remember, so nu of G is the size of so it's the max size of a matching in G. Remember, matching is just a set of disjoint edges, so edges that don't have any endpoints in common. And tau of G is the min size of a vertex cover. And remember, a vertex cover is a set of vertices that hits all the edges, right? So every edge has an endpoint in the vertex cover. So now let me give you a proof of this. Any questions about the statement before I go on? Right, so this is actually kind of nice proof. So one direction is something we already know, right? So we already know. So this was the first thing I proved yesterday, that one inequality holds. So nu of G is certainly at most tau of G, because this actually holds for all graphs G, right? So this is nothing special about bipartite graphs. This holds for all graphs, right? This inequality. The special thing about König's theorem is that you actually have that they're equal. Okay, so all we need to do, so to prove equality, all we need to do is find a vertex cover. So I'll kind of denote that, I'll shorten this to Vx for vertex of size nu of G. Right, so if we can find one of that size, then these two things have to be optimal or they have to be equal. Because that would give me that tau of G is at most nu of G, because I found one of that size, and combining the two inequalities would prove equality. Okay, so what we do first, a natural place to start is just to take a biggest matching, right? So let M be a matching of size nu of G in G. So it's the biggest possible matching. And now what I'm going to do is I'm going to just basically write down what the vertex cover is, but then we're going to take it's going to take a few arguments to just prove that it has the properties that we want. But it turns out it's not hard to just kind of write down what it is. So define U to be the set of all. Oh, right. So remember, G is bipartite, so it has a bipartition. So maybe I'll say let AB be a bipartition of G. all the edges go from A to B. So now we define U to be the set of all vertices in A such that they're not saturated by the match. So V is not saturated by M. Remember, okay, I mean, I'm kind of just using a bunch of terminology from yesterday, right? But just to remind you, so saturated, so a vertex is saturated if it's included in one of the edges of M. So it's saturated if and only if it's in a matching. So these are the things that are the vertices that are not hit by the matching. And now I'm going to define Z to be the set of all vertices, say W graph, such that there exists an alternating path, so an M alternating path, starting in U and ending at W. Remember, M alternating means it's a path where the edges, the first edge is, okay, it's either in M or not in M. The next one is the opposite of that, and so on. It alternates between being in the matching and not being in the. So these are all the vertices that you can reach by starting somewhere in U and doing an alternating path. And notice that these W, they can be either in A or in B. So now I can just literally write down the vertex cover, but I'm going to have to prove that it has the properties we want. So A is the set, C is the set A minus Z union B intersect Z. So I claim that this is going to be a vertex cover and that it has the same size as the matching. So is it clear any questions about anything? So I need to prove now that, remember, my whole goal is to find a vertex cover of size nu of G. And so that's the same size as it, right? So I claim that C is the vertex cover that I want. So what I need to prove are these two claims. So first I need to prove that C is a vertex cover. So I'll call that claim 1. And claim 2, I need to prove that the size of C is the same as the size of M, which is, of course, the same as nu of G. And then I'll be done. Okay, so let's prove the first claim. Okay, so for this, it's maybe helpful to draw a little picture. So I've got the set A, I've got the set B, I've got A intersect Z, so an A minus Z. So of course this partitions A, and I've got B intersect Z, and I've got B minus Z. Right, and the set C that I chose, so by definition, the set C is the stuff which is here, the stuff. So this is the set. That's the set C. A minus Z, B intersect. Okay, so I want to show it's a vertex cover. So in other words, I want to show that all the edges in the whole graph must have an endpoint either here or here. So in other words, I need to show that there doesn't exist an edge, let's say xy, which goes from here to here, right? So this is the only kind of possibility where I could have an edge that isn't covered by this red set, right? It would have to start here. So I need to prove that there's no edge with x in A intersect Z and y in B minus Z. Is that clear? Okay. But this is basically just going to follow from the definition of Z. But the bipartiteness actually matters here. So there's a sort of parity thing that you have to think about. So suppose that such an edge, exists. So suppose such an edge xy exists. Well, okay, so what's the, what do I know about x, right? X is in A intersect Z, so I know that there's some sort of alternating path which starts in U and ends on that vertex, right? So there exists a path where this guy's, I'm going to call him V0, he's in U. Maybe I'll draw to X, where it's alternating. Okay, so it's M alternating. But so how does that path have to look? So if I draw the matching, if I draw the edges of M in blue, they're going to be blue. Well, the first edge can't be an edge of M because V0 is in U. So it's not, oh yeah, okay, sure, yeah. How about yellow? Yellow's usually, so M is going to be yellow. Okay, so the first edge definitely can't be a matching edge because U is not saturated. So since this is alternating, it must be, so this edge must be in E minus M, and the second edge must be in M. And so the fourth edge is in M, and so on and so forth. And what else do we know? So we know that by definition of U, the first vertex here is in A, right? Because U is a subset of A, so therefore B0 is in A. And I know that all the edges in the whole graph, every edge goes from A to B. There's no edges that stay inside of A. So therefore, the second vertex, V1, is in B. Right? So this guy's in A, this guy's in B, this guy's in A, that guy's in B, because all the edges go from A to B. And kind of by parity, so you know that, just because the edges always alternate from not in M to M, the vertices always alternate from A to B, so you know that this kind of pattern continues, right? So the edge that comes before X, this edge must be, because X is in A, this must be in E minus M. And the edge before that has to be in M. Yeah? Yes. Okay, yeah, no, you're right. Yes, that's good. Okay, this is better. Thanks for pointing that out. Sorry, I messed that up. So the last one has to certainly be M. The second last one is in E minus M, right? Because that's how this pattern goes, right? An edge from B to A is in M. Thanks. Okay, so now but now take this edge from X to Y, right? Remember we started by assuming that there's some edge, so this was X and this is Y, but now we get a contradiction, right? Because, so this last edge is certainly not in the matching because it's a matching, right? If this was in the matching, you'd have this vertex having two matching edges, right? Both of these would be yellow. That would be a problem because matching edges have to be disjoint. So this is definitely an E minus M. And now this gives you, so the existence of this path tells you that Y has to be in Z, but that's a contradiction because we already know that Y is in B minus Z, just by definition. So there certainly are no edges from this set to this set, so therefore this red set is a vertex cover. Any questions about that? There's one minor technicality that, okay, technically, so if I have this path, and it's not necessarily a path if I add Y, right? Y could have been one of the vertices back here. So that's one small technicality. But then obviously you'd get just a shorter alternating path that goes to Y. Well, that would be a problem already because so this edge is in M. If this one was also in M, then they wouldn't be disjoint. Because in a matching, you never have two edges in M which share a vertex. They always have to be disjoint. So if that one was in M, either it would have to be the same edge as this, in which case, well, you just have a shorter alternating path to Y, or it'd have to be a different edge, but then they intersect. Okay, so this one is in E minus M because M is a matching. It's just right from the definition of them. I'll send this up. Okay, I still have a lot. Okay, so now, that proves claim 1. Now I need to prove claim 2. So I just need to prove, so the contradiction would be, you mean the very final contradiction? Or so the final contradiction is that we've now, by we took an alternating path that ends in X, and we were able to extend it to Y. That would imply that Y is in Z, by definition of Z. Right? Z is all of the things that can be reached by an alternating path, starting in U. But by assumption, Y was in B minus Z. You can't be in Z and B minus Z. Okay, so now let's focus on the second claim. So I want to show that the size of C is the same as the size of M. What we'll prove, so it'll be enough to show the following two things. So A, we want to show that every edge in M contains a unique element of C. And secondly, that every vertex of C is contained in some edge in M. If this is true, then this sets up a bijection between M and C, right? So if A and B hold, then the function where I f from M to C, which maps each matching edge to a vertex that's contained in it, is going to be a bijection, which maps E to vertex contained in it is a bijection. So that would imply that the size of M is the size of C. Was there a question? Right, because it's not hard to see. Oh, here I'm subtly, so for the injectivity of F, somewhat subtly I'm using the fact that M is a matching. So if F wasn't injective, two matching edges would pick the same vertex, but that vertex would be in both of the edges. And that's not possible in a matching. Okay, we're almost done. So proof of A. So what was A again? It's that every matching edge has only one every matching edge only gets hit once by the elements of C. So, okay, so if it wasn't true, so if not, then there's some matching edge xy, so then there exists xy in M with x in A minus Z and y in B intersects Z. Right? Because that's, remember, all the edges go from A to B, and the only way to have two endpoints, both in C, is you have to go from A minus Z to B. But the proof of, so the fact that this gives a contradiction again, and the proof is really the same as what we just did, basically. So then, taken an M alternating path from some vertex of U to Y, extend it to Z, or sorry, to X, just by taking this edge XY. So therefore we get that X is in Z because we get a longer, an alternating path that starts at U and ends at X, but that's a contradiction because X was in A minus Z. Right? So I'm not going to go through the details of this because it's really the same proof as that one. Take this path and you just extend it using the matching. Okay, so that was okay. How about proof of B? So what is B? So we want that every element of the cover, every element of C is in a matching edge. Well, this is actually pretty easy. So suppose, so again, we're going to do it by contradiction. So suppose that some X, so remember C is the union of two different sets. So first I'm going to consider X in A minus Z. So suppose that he is not in a matching edge. So, okay, an easier way to say that is actually just saying he's not saturated. Right? Saturated is the same thing as being in a matching edge. But then X is in U. Right? That's the definition of U. It's the things in A which are not saturated. But then the trivial path from, I perhaps should have done things a bit more carefully. Because technically, I guess the trivial path from X to X is technically not alternating. Because I think alternating paths, they should have length longer than. So, okay, so going back to the definition of Z. So apologies for this. So I want to take Z to be, this thing, union, the set U. So the elements of U are also in Z. Sorry to make you go back in your notes to add that. Apologies. So given this small modification, right, now we get a contradiction because U is now contained in Z, right? But that's a contradiction because literally we said that X is in A minus Z. And the other direction is not any harder. So suppose that Y in B intersects Z. Actually, this is the first time we're going to use augmenting paths. So is not saturated. Actually, so far we haven't even used the fact that M is the biggest matching. We've never, so far in the whole proof, we never used that. This is the only time we use it. So if you had some guy, Y, in B intersects Z, that's not saturated, then we know that by definition of Z, there exists an M augmenting path from some U to B, to Y. Technically there's an M alternating path from there, but then it's augmenting because U is not saturated by definition, and neither is Y. So therefore, M augmenting, and if you just switch the edges on that path in the usual way, so that would imply that M is not max size. Sorry about this writing, and that's a contradiction. So that completes the proof. Remember, augmenting path, it's alternating, and the endpoints are not saturated. Any questions about any of this? Okay. So the last thing I want to do today is give you an algorithm. So remember, in combinatorial optimization, we're not just interested in being able to solve problems, but you want to be able to solve them quickly and efficiently. Well, quickly, efficiently, same thing in this context. Okay, so remember, so generally we want to find big matchings, right? For example, if you have some bipartite graph which corresponds to workers and jobs, where an edge is people who are qualified for the job, you might want to match up as many people with jobs as possible, right? That seems like a logical kind of goal if you want to get people employed, right? So you want to find big matchings. And we want to find, in particular, we want to find maximum size matchings efficiently. remember, though, that if you have a matching, it has maximum size if and only if it doesn't have an alternating path, right? So basically, if we can find alternating paths quickly, then we can always increase a matching quickly, and this will kind of lead to getting the biggest one quickly. So it suffices to find augmenting paths efficiently. Or when I say find, I mean either you find one or you can output that none exists. You want to be able to decide whether it exists or not. So there's an algorithm to find augmenting path in a bipartite graph, or to show that, or to show that none exists. So you want to be able to do both, right? In time big O of the number of edges. Oh, I should write M augmenting. So here I'm thinking there's a graph, a bipartite graph, and there's a fixed matching. And what I'm saying is that there's a fast algorithm to see, does it have an augmenting path? And if not, it can tell you it doesn't. Is it clear what this statement is saying? Any confusions? Yeah, so this algorithm that I'm going to use, so if you want to look in the notes, this is from the notes of Shriver, section 3.4. So there's lots of different algorithms for this, but this is the one I'm going to use because it's really nice and easy. Okay, so here's the algorithm. Well, so first we're going to kind of do some processing to the graph. We're going to kind of change it into a directed graph. So define a directed graph, so a digraph D, where, well, the vertex set is just V, so it's just the original vertex set of the graph, and, well, the set of arcs is going to be basically the same as the set of edges of G, but we're going to choose a direction for each arc. So where for an edge of G, D contains the arc from X to Y, so this is the arc kind of from X to Y, like this. If XY is not a matching edge, and the arc from Y to X, sorry, this doesn't make any sense how I've written this. So let me add something here. So this is an edge of the graph where X is in A and Y is in B. Otherwise, this doesn't. So it contains the arc YX if XY is in the matching. Now the key observation here, so the key observation is that, actually, so now I need another definition. So let A prime, the set of unsaturated vertices A, and similarly B prime is the set of unsaturated vertices of B. So the key observation is that an augmenting path is actually the same thing as a directed path which starts in A prime and ends in B prime. Okay, sorry about this blue light. It's going to turn. I've just got a few minutes, so I'm not going to play with the electronics. Okay, so the key observation is that a directed path from somewhere in A prime to B prime is exactly equivalent to an M augmenting path, is the same as an M augmenting path. Right? So if you have such a directed path, you can check it's going to be augmenting, and like vice versa. If you have an augmenting path, it's going to give you a directed path in this graph, or digraph. Okay, so basically all we have to do is use an algorithm. We just need to be able to check, is there a directed path from A prime to B prime? So the algorithm basically is just going to kind of explore the graph, or the digraph. So you start with, so I'm going to call S0, that's kind of the starting set of the things we can reach from A prime. So it's just going to be A prime. And then basically for I at least 1, let Si be the set of all vertices that you can reach from Si minus 1, right? So it's going to be the set of all, well, vertices that you haven't seen yet, such that there exists some way to travel there from your set. So there exists x in Si minus 1, such that xv is an arc. Right? So you start with A prime as 0. You look at all the ways to travel out of A prime as 0. And this set of things is going to be S1. You look at all the ways to travel outside of here. That's going to be S2, and so on. So if you ever get to a case where this Si contains, so if Si ever contains a vertex of B prime, then we stop and we output, we found an augmenting path. So I know I'm not being perhaps completely technically, perfect here in describing this algorithm, but this is perhaps a bit sloppy, but I don't have a lot of time. But anyway, but you can probably imagine this algorithm, right? You start with your set A prime, you kind of build outwards to all the things you can reach. If you ever reach an element of B prime, the reason you did was because there's some sort of directed path. And then if you end up where at some point you just can't reach anything else, you stop and you can say that there's no augmenting path. Okay, so, and then if you think about it, you can implement this algorithm in a way that it only uses big O, the number of edges steps. Okay, so then, right, so now we get an algorithm for finding the biggest matching in a bipartite graph. So, but it's probably time to go, isn't it? Let me just take 10 more seconds to write this. So, largest matching algorithm in bipartite graphs. So now that we can find augmenting paths, it's pretty easy, right? So initialize. So initially, we just set M to be the empty set, and then while the size of M isn't too big, or isn't, let's say, the size of M is at most the minimum of the size of A and the size of B, because, well, certainly you can't have any matching with a bigger size than this because there just simply wouldn't be enough vertices for it. So run augmenting path algorithm. If no augmenting path, then you know its maximum. If there is one, so we can find a bigger matching. Right? And then we call that bigger matching M, and we go back here, and we keep running this. So this has running time. If you think about it, it's big O number of vertices times the number of edges. Each iteration takes big O the number of edges steps, and there's at most number of vertices, big O the number of vertices iterations, because the matching can only increase that many times. Okay, so that's all for today.